Welcome to the 15-minute Safety Connect webinars from DuPont. These are short webinar episodes of 15 minutes, giving you essential information on a topic linked to safety. My name is Chloe Wetherell. I am the EMEA Channel Marketing Manager here at DuPont Personal Protection, which is the unit within DuPont focusing on protecting people at work. And I have the pleasure to be hosting these sessions together with two of my colleagues. So I'd like to introduce you first to Figen Ersezer, who is our EMEA and user marketing specialist, and also to Steve Marnach, who is our training manager for the EMEA region. The session you will be viewing today has been pre-recorded. However, you can send us your questions via the functionality which you will find on the side of your screen. And we will make sure to answer all the questions we receive just after the webinar. In the meantime, I would like to wish you a very nice webinar. We hope to see you also for the next sessions. Enjoy.
Thank you, Chloe. Today we will be covering the thermal hazards, and we'll first start by defining thermal hazards in themselves. Then we'll have a look at the thermal protection norms, and finally conclude as usual with the takeaways. So what do we exactly mean when we are talking about thermal hazards? Well, in fact, thermal hazards are all types of threats that can lead to skin burn injuries. Now that these can be linked to cold, radioactivity, sun, etc. But in this webinar, we are just focusing on two main hazards because that's the hazards where thermal protective apparel will protect you from, and they are also the most frequent in the industries. And these are fires and electric arc. Now, these two hazards are completely different. You can see an electric arc is happening when there's a fault in the electrical installation, and then an electrical arc is created by the energy, which will lead to an expansive explosion, melting all the parts of the electrical installations, create very intense heat of up to 10,000 degrees centigrade and more during an extremely short time period of a few nanoseconds only. A fire, on the other hand, is completely different. As, for example, when you have excessive fuel that starts burning all of a sudden when it has a source of ignition. It is considerably less heat intense than an arc flash, having a maximum temperature of 800 to 1000 degrees C, but it can last significantly longer and spread much faster than an electrical arc does. And that's the reason why there are different norms and standards for these two hazards, because by nature these events are totally different. So it makes sense standards to evaluate the garments against. For the fire hazards and all linked hazards like molten metal splashes, contact heat, etc., you have the ISO 11612 in Europe which are covering that. So there are a series of tests run under ISO 11612 that we will detail in a few minutes. For the hard electric arc hazard protection, you have a global standard in the IEC 61482-2, which is allowing two ways of measuring or testing the garments rather. That's the open arc and the box arc testing methods that we will detail as well in a few minutes. Let's first start with the ISO 11612 for the flame protection, etc. So the 11612 is detailing all the level of tests that should be done on the fabric samples only. Now you see that there's only one of these fabric tests that is mandatory, and that's the limited flame spread identified by the code letter A, according to EN ISO 14116 from 2015. And then you need to do one of the other fabric tests. One of them is mandatory, but you can choose which one you want to do, but you can also do them all, of course. And these are convective heat, identified by the code letter B, radiant heat, identified by code letter C, molten metal splashes, identified by the code letters D and E, and then finally contact heat with the code letter F. Now, as I said a few seconds ago, these are all fabric tests only, on pieces of fabrics, not on full garments. There is one optional test for testing the performance of complete garments, and that's the thermal mannequin test. Now, as I said, this is optional, it's not mandatory, but it's a very interesting test, as you will see as well in a couple of minutes. But first, let's start with the mandatory test, and that's the limited flame spread test. So here you see a graph of the and a picture of the buildup of these testing methods. So what you're doing is you take a Bunsen burner and you put it during a short period of time in contact with the fabric you want to test. And then you're removing the burner and you're evaluating how the fabric performed. As you see in the table on the left side of your screen, there are 3 index levels of performance with varying requirements. Now, in order to have a limited flame spread approved fabric, you cannot have any flame spreading, of course. So meaning the material should not burn by itself once you have removed the Bunsen burner. You shall not have any flaming debris neither. And the afterglow should be last lower than 2 seconds. Now, the distinction between the 3 levels of performance are determined by the hole formation and the afterflame. While you can have a hole formation and an afterflame for index 1, you are not allowed to have any hole formation for the indexes 2 and indexes 3. While you can have an afterflame lasting longer than 2 seconds for the index 2, you must be below the 2 seconds for the index 3. There are 2 ways how you can test the fabrics. You can either use the surface ignition testing by putting the Bunsen burner straight onto your fabric, or you can do the edge ignition, which is procedure B. Both are shown on the pictures on the graphs rather on the right-hand side of your screen. So that's the only mandatory fabric test according to the standards. Now, the other test you can freely choose from, but before we go to that, I will show you some pictures of how different materials perform during that testing. So you see here the difference between cotton and an FR material, whereas the cotton instantly catches fire and keeps on burning even when you have removed the Bunsen burner. With an FR material, a flame-resistant material like Nomex, that is not the case, as you see in the lower side of the picture. You have just the color that has burned, but once you remove the Bunsen burner, you see that the material by itself is not burning. So after the 10 seconds flame, you will check if there's a hole formation, if there's a flaming, if there's debris, an afterflame or an afterglow, and you assess your material according to its performance. Now let's move to the other tests, which are freely to choose from or can be done all. And I will start with convective heat, which is identified by the letter B and is defined by ISO 9151 standard. So here you see both a picture and a graph of the testing methods. So you put the sample you want to test below a calorimeter, and below your sample you are creating a heat source of 80 kilowatt per square meter using the device below, and then you're measuring the time it takes for the temperature on the calorimeter to rise rather to the level of pain or to the level of second-degree burns. Now, the level of pain is the moment in time where you feel the heat of the burn without having sustained a skin burn, a skin injury already. And that is happening when the temperature on your skin has increased by 12 degrees centigrade. You only get a second-degree burn once your temperature has increased by 24 degrees centigrade on your skin. And for rating the performance levels of convective heat, that's exactly the point that you're going to take. You're measuring the time in seconds it takes to raise the temperature by 24 degrees centigrade, in other words, which would lead to second-degree burns. And then you get the performance level between B1, the lowest, and B3, the highest. Now, if it takes more than 4 seconds, but less than 10 seconds to achieve this point of burn, then you have a B1 level of performance. If it takes between 10 and less than 20 seconds, you have a B2 performance. If it takes longer than 20 seconds to achieve the level of pain, you have a B3 performance in the convective heat test. Then the next test I want to show you is the radiant heat test methods, and this is identified by the code letter C. Again, here you see a graph and you see a picture of the equipment. So you have a heat source of heated metal rods that have a temperature of 1100 degrees centigrade on the surface, and you have at a certain distance both the sample of your material you want to test and your calorimeter that is measuring the temperature, and between the two you have a radiant heat of 20 kilowatt per meter square. And here the same principle than before, you're measuring the time it takes for the calorimeter to detect a temperature if you increase of up to 24 degrees centigrade. In other words, the point of skin burns. And then you rate your performance levels based on that into levels C1 to C4. Again, it's the same principle as you can see here on the table. If it takes more than 7 seconds rather and less than 20 seconds, you have a C1 performance. And if it takes more than 50 seconds and less than 95 seconds, you have a performance level C3. Now, the molten metal splash test is a little different in nature, and this is identified by the code letters D for molten aluminium and code letter E for molten iron splash. Now, the test setup is demonstrated here in the graph on the left-hand side of your screen. What you're doing is you're pouring a predefined quantity of molten aluminium or molten iron onto your material you want to test, for example, Nomex, and beneath that layer of Nomex, you have an artificial skin that is reacting more or less like your skin would do if you pour molten metal on it. So you're checking if this artificial skin is sustaining any damage or not after having been exposed during 30 seconds or a predefined quantity of molten metal. Now, this is a pass-fail test, and you always start at the lowest level. For example, at the molten aluminium splash, at the performance level D1, you take 100 grams of molten aluminium that you're pouring on your fabric, on your Nomex, for example, and you wait for 30 seconds, and then you're checking if your artificial skin has been damaged or not. If it's not damaged, you pass already the level D1. And then you take a new piece of fabric, a new piece of artificial skin, and then you do the same test, but this time with 200 grams of molten aluminium splash. If you pass this, you have the level D2, and you go to the 350 grams that you're splashing onto your Nomex. However, if you fail the level D2, meaning if after having poured 200 grams of molten aluminium onto your material, then you have failed level D2, but you have successfully passed level D1 before, and that's why the definition of D1 is more than 100 grams of molten aluminium, but less than 200 grams of molten aluminium, because that would equate to level D2 already. And the quantities for iron may be different, but the principle is exactly the same. And you see the different performance level on the chart. Now, the last fabric test that you can choose from is contact heat, identified by code letter F. Here you have a heat source of 250 degrees centigrade. You put your material onto that, and then with a gap of 10 millimeters, you have a sensor below, and you're measuring a temperature, the time it takes to have a temperature, the increase of 10 degrees centigrade, so well below the point of pain. And here you have, again, 3 performance levels, F1 to F3, and the test goes like that. If it takes more than 5 seconds, but less than 10 seconds to have a temperature increase of 10 degrees centigrade, you have level F1. If it takes between 10 and less than 15 seconds, F2, and if it takes longer than 15 seconds of contact heat, you achieve level F3. Now, you may wonder why there's a gap of 10 millimeters between the fabric and your sensor. Well, very simply, because there's always a gap between your skin and the garments you are wearing. And typically that's a more or less 10 millimeters. So you may be in direct contact with a hot pipe, for example, but below, unless you're really kneeling and exerting pressure on it, you'll have the gap between your fabric, your garment, and your skin, hence the 10 millimeters. Now, as I said, all these tests are done on fabric samples only. So you're not getting a real assessment of a full garment. In order to assess a full garment, the mannequin test, according to ISO 13506, is a very good method indeed, because here you can dress a mannequin with the garments you want to wear, and you are exposing that to a full flame engulfment between 3 and 20 seconds. The industrial standard in Europe is 4 seconds. And you generate heat and flames with 12 propane burners that will fully engulf the mannequin, generate a heat between 600 and 1000 degrees centigrade inside the chamber. And you're measuring the heat going through the garments with the 102 heat sensors that are a little bit everywhere on the mannequin. Now, with that, you really get concrete data. You will see what is the level of second and third degree burns sustained after such a flash fire exposure. You see where the burns happened. And with the translation according to the Stoll curve, you also see the chances of survival based on the burn rate injury that would have been sustained in such a case. I will now pause a minute. I will show you a video on our thermoman testing methods that we have at DuPont.
Developed by DuPont and the US Air Force, Thermoman is built inside a container for conducting tests simulating the garment's exposure to direct fire with temperatures up to 1200 degrees Celsius. DuPont Thermoman is a life-sized mannequin equipped with 122 heat sensors. The sensors record the temperature rise on the surface of the mannequin. The computer calculates the predicted percentage of second and third degree burn injuries a person might suffer under similar conditions. Tests show that with exposure to the same flash fire, a worker dressed in cotton or polyester cotton could suffer combined second and third degree burns over up to 90% of his body. While for a worker protected by Nomex, the potential injury level could be contained to less than half, resulting in a lower degree of burn injury over a smaller body area, and thus substantially increasing his chances of survival and reducing recovery time.
Now that was interesting, wasn't it? Let's now move over to electrical arc protection, which, as I said, is a completely different hazard and also a different set of standards. In order to determine the incidence of electric arcs on PPE, the IEC 61482-2 is allowing two testing methods, the open arc test and the box test. There are two different concepts. While the open arc test is one with an energy that can be determined based on the residual risk that you may be facing in your electrical installation, you will be getting an arc thermal performance value, ATPV, in calories per square centimeter, which is indicating you the level of energy the garment can protect against. You will also have the break open threshold energy, which is also giving you the indication at what point in time the garment may break open. Now, the box test is a completely different test methods where you have only a pass-fail criteria and two levels of energies that are being used for measuring that. You have 4 kiloampere for class 1 and 7 kiloampere for class 2. I will detail the two testing methods in a minute, and I will just conclude by saying that the hazard assessment can be linked to the open arc test, but not yet for the box test. At DuPont, we not only have the Thermoman, we also have the Arcman. And again, I will pause in order to share you a video on our Arcman.
Located in Switzerland, the CEF facility is fairly unique, not only in Europe, but also in the world. Approximately 60 kilometers away from the DuPont Technical Center, the CEF laboratory can generate up to 100,000 amps. DuPont has only one device in the world, but is also the only producer of high temperature resistant fibers that have these performance capabilities. There are only 3 open arc testing laboratories in existence in the world that follow the current international testing guidelines, which are located in Spain, Canada and Switzerland. At CEF, a collection of rotating machines, alternators and generators, with the most powerful being 500 MVA, almost 1/3 of a nuclear plant's capacity, are used to generate a very high level of current. This enables the laboratory to be totally disconnected and free from the grid while generating high currents. Therefore, there is no problem with the electricity supply to the surrounding area. The rotor weighs 20 tons. This allows for the accumulation of kinetic energy and its transformation to electric energy. The DuPont Arcman is a device for evaluating the thermal effect of an electrical arc on fabrics and/or garments. An electric arc is generated at the center of the cage, which enables us to expose the specimens to a high level of energy such that could be created during an incident in an electrical system. The open arc test determines the limit of the incident energy up to which a material or assembly will provide protection against the thermal effects of an electrical arc. The electrical arc is instantaneously ignited through the help of a 30 centimeter fuse wire laid across the gap between 2 stainless steel electrodes, which are positioned in the center of the test rig. The test voltage needs to be sufficient in order to maintain an electrical arc across the distance between the electrodes during the tests. This is typically between 2 and 4 kilovolts. The voltage drop along this arc is typically between 400 and 700 volts. The duration of the arc will vary for each test shot, from test shot to test shot, from 120 milliseconds to 2 seconds, in order to achieve the required incident arc energy. Tests are to be carried out on fabrics to determine the arc rating, giving ATPV or EBT values, or on garments to assess the arc effect on accessories such as sewing threads, logos, reflective tapes, and so on. We have a Tandberg equipped conference room to which you can connect to experience live test sessions.
Now that was even more impressive, wasn't it? Let's now move over to the arc-in-a-box testing method, which is orienting the electrical arc, as you can see on the pictures and on the graph. So the idea behind this testing method is that for a lot of accidents, they typically happen when an electrician is working on a small electrical installation, household level appliances, etc. So typically the arc is always hitting the chest of the electricians. And that's what we are doing here with the arc-in-a-box test method. So you are generating an electrical arc inside test box, and you're orienting it towards the mannequin that is wearing the jacket. And then you're seeing and you're checking if the garment will be broken open due to the electric arc or not. So it's a pass-fail criteria. And the level of energy that you use for making the electric arc is either 4 or 7 kiloampere for class 1, respectively class 2. You are not getting, contrary to the open arc testing method, any indication on the burns that would have been sustained. Now, that's all that we had for today. Let's see what we went through today. First, we focused, laser focused rather, on the 2 main thermal hazards that you're seeing in the industry: heat. norms and standards for these two hazards. And then we showed you some testing methods that allow you to assess full garments and not only pieces of fabrics in order to make sure that your workers stay protected at all times, because we are not just wearing pieces of fabric, we are wearing full garments. Now, that's all for today. I will now hand over to Vigen, who will explain you the process how you can ask.
With this, we conclude the session for today. If you have any questions, please use the chat function on the side of your screen and send your questions to us. We'll come back to you very shortly. And thank you very much for watching us today. We hope you enjoyed it, and please stay tuned for the next 15-minute Safety Connect.